Welcome to Chapter 17, Physics 105, Change of Phase. Okay, we're going to talk about change of phase and the type. And of course, in order to do that, we have to talk about the phases of matter. And we're going to talk about how matter changes phase, evaporation, condensation, boiling, melting, freezing, and also the energy changes that are involved in the change of phase. Most people think matter exists in three common states. In reality, it's four. Solid phase, a good example of that, as I said, exists at the lowest temperatures. Then the liquid phase, of course, that would be water, that exists at the next lowest temperature. Then the gaseous phase, that would be steam or vapor, exists at the next lowest temperature. And then finally, the highest temperature is the plasma phase. And that's where the vapor disintegrates into ions and electrons and becomes electrified. In reality, the plasma phase is the most common state of normal matter in the universe. Most of the universe, this normal matter, is plasma. Now, as you probably guessed, the phase of material depends upon the temperature and pressure. When a material undergoes a change of phase, like from the solid to the liquid to the gas to plasma, you have to heat it up. You have to add energy to the material. And what this does is it causes the molecules to move more rapidly and breaks the bonds between them. If you go in the opposite direction, you probably guessed, plasma, gas, liquid, and solid, you have to take energy out of the material, and this lets the molecules slow down and allows the formation of bonds. Now, evaporation, we're going to do a couple of examples of this. Evaporation is this change of phase from liquid to gas. And of course, it's the opposite of condensation. And basically what happens in evaporation, here's the liquid. Some of the molecules leave the liquid and become vapor. The opposite is condensation, where some of the molecules leave the vapor and go back to the liquid phase. So what happens in the liquid is all the molecules are moving randomly at various speeds, and they collide with one another. And in a collision, some molecules will gain kinetic energy, others will lose kinetic energy. And the ones that gain, if they gain enough of it, they can become energetic enough to escape the liquid and become a gas. And of course, that takes their kinetic energy away from the remaining kinetic energy that's in the liquid. So it has a tendency to decrease the energy, overall energy, and that results in a cooler water. And so evaporation is a cooling process. And it's important to us. Okay, have you ever heard, I'm hot and sweaty today? We produce sweat. Sweat is water. And water on our skin will absorb body heat as it evaporates and takes the body heat away from us. It helps us maintain a stable body temperature, but not all animals can sweat. Pigs can't sweat. They don't have any sweat glands. They like to roll in cool, damp mud, and that allows them to keep cool. And dogs, of course, they have sweat glands only in their feet, but they cool off by panting. And by panting, they allow water from the lungs to evaporate, which cools them from the inside out. It's actually very effective. Now, sublimation is a phase change directly from solid to gas. Dry ice, you've seen dry ice sort of disappear, or mothballs. You leave mothballs out, after a while they get smaller and smaller. Or even water, frozen water, ice cubes will disappear in the refrigerator. A snowbank, even though it's below freezing, will get smaller and smaller as time goes on. This is all examples of sublimation. The opposite of that is a formation of black ice on roads, or frost on windshield, or frost in old-fashioned refrigerators that you have to defrost manually. Now, condensation is the opposite of evaporation. It's a change from gas to a liquid. And what's going on here is the gas molecules near a liquid surface are attracted to the liquid. And they strike the surface and stick, and then become part of the liquid. And they give up some of their kinetic energy to the liquid, and that warms the liquid. Now, condensation is, of course, kinetic energy is absorbed by the liquid. That increases its temperature. We're going to find out steam has a huge energy of vaporization. So steam releases a lot of energy when it condenses to a liquid and moistens the skin. So if you get a steam burn from 100 degrees C, it's generally more damaging than a water burn from 100 degrees C water because the steam has more energy to give up. You also will feel warmer in a moist shower stall because what happens, the humid air, the rate of condensation in the humid air of the shower stall will exceed the rate of evaporation, and condensation is a warming process. You will feel hotter on humid days than on dry ones because, again, humid days have more water vapor in the air, so you're more likely to have condensation occurring on you rather than evaporation occurring from you. And when cities are dry, you have a cold, dry day, okay, or a cool, dry day, or even just a warm, dry day, the rate of evaporation from your skin will be greater than the rate of condensation, so you feel cooler. In humid cities, just the opposite. The rate of evaporation from your skin is less than the rate of condensation, so your tendency to feel warmer. And that's the old saying, it's not the heat, it's the humidity. Yeah, and if you've ever left a cold drink out in warm, wet air, the drink gets wet on the outside from condensation. The slow-moving molecules in the vapor in the air make contact with the cold surface and condense. So when the temperature of the atmosphere is low, condensation can also occur not just on surfaces, but up in the atmosphere. When the temperature of the atmosphere is low, the water molecules in the air will move more slowly, and then they have a tendency to stick together, and then they condense into little tiny droplets. Oftentimes, dust particles are in the air, and they can also serve as nucleating bodies around which the water molecules can condense. And this is how fog and clouds are formed. Fog and clouds are basically the same animal. Fog is a cloud that's on the ground, cloud is a fog that's in the air. And they're basically created from the water vapor in the air, the humidity when the air cools. You've also noticed this when you go outside on a cold day and you breathe outward and you see your breath. Okay, that's basically the formation of fog from the moisture in your breath. Now, these check your neighbor questions. You should answer just like we've been doing. You should answer these at home in your class notebook, and then use the lecture videos to find out what the answers are, make any corrections. If you miss a lot of them, you should study, go back and read the chapter in the book and maybe do a little bit more studying. Remember, the odd number of questions in the back of the book are answered, so you can do even more practice there. If you got a lot of them right, then maybe you don't need as much practice, but you still have to review. Okay, if bits of coals do not stick to your feet when you're firewalking, if you don't want the bits of coals sticking to your feet and burning you, you definitely want to have your feet wet, because the energy that vaporizes the water is energy that doesn't burn your feet. And of course, if the coal doesn't burn your foot, it's less likely to stick anyway. When you step out of a hot shower, you feel cold, but you can feel warm again if you step back in the shower. What process is responsible for this? It's actually condensation, because the humidity, the water vapor that's in the shower, is higher. It will condense on your body, causing it to warm up. Now, boiling is evaporation on steroids. It's basically rapid evaporation, and it kind of occurs from beneath the surface of the liquid. You can see this if you look down at a boiling pot of water. You see the bubbles come up, and then sometimes they collapse again, but they actually form in usually close to the bottom of the pan where it's hottest. And this occurs when the temperature raises the vapor pressure enough to overcome the ambient pressure of the liquid. So what happens is, as you raise up the temperature, heat this up, the water kind of gets warmer and warmer, and it becomes less dense, so it rises and forms these convection currents in here. And as it warms up more and more, vapor pressure is related to the temperature of the fluid. So as you warm up the fluid, the vapor pressure gets greater and greater. Eventually it gets to the point where it's enough to overcome the ambient pressure in the fluid, and the bubble will form. As steam bubble will form in there. As this rises, sometimes it rises into cooler water that's up here, and this bubble might collapse again, or it might make it all the way up to the surface. Rapid evaporation beneath the surface will form vapor bubbles. The bubbles are lower density, so they tend to rise to the surface. They're buoyant. If the vapor pressure in the bubbles less than the surrounding pressure, then the bubbles collapse before reaching the surface. They condense again and collapse. But the vapor pressure rises with temperature. So the bubbles don't form a temperature below boiling point because the vapor pressure is insufficient. When the temperature rises to the boiling point, then the bubbles make it to the surface and the liquid boils. We call a full boil or a rolling boil. Now, boiling water 100 degrees C is in thermal equilibrium. So in other words, you got as much heat coming in as leaving. So the water's being cooled as fast as it's being warmed. Boiling is basically a cooling process, like evaporation. It's basically the same process as evaporation. And the steam is higher internal energy than the water and takes its energy leaves the water. So it cools off the water left behind. But you keep adding energy in, so the water never stops boiling. And of course, you notice this. You turn off the stove. What happens immediately? The water stops boiling almost immediately, because this is such an efficient way of removing heat. Okay, now as I mentioned before, the boiling point depends on pressure, the external pressure. This is why pressure cookers are so cool, or warm. Okay, what they do is they put the fluid inside an enclosed vessel, okay, pressure vessel. And when you heat it, it builds up the pressure inside. It'll be higher than the atmospheric pressure. So the water will boil at a higher temperature. That higher temperature allows the food to cook more quickly. On top of that, on the other end of the scale, you may have noticed that maybe on the back of packages, they tell you the cooking instructions for some things. And they might say if you're above a certain altitude, you have to cook it longer. That's because the boiling pressure drops with atmospheric pressure. And as you get higher up in the atmosphere, that atmospheric pressure drops, so does the boiling temperature. 95 degrees C in Denver, Colorado, water is boiling. At sea level, it boils at 100 degrees C. So this is the reason I've been saying all along, standard pressure. Now, it is possible to take room temperature water, put it inside a vacuum jar, suck out all the air. And of course, what that does is it lowers the vapor pressure by just pulling the air out of it. External pressure is lowered. And eventually the water will get to the point where the vapor pressure exceeds the lowered pressure and the water will start to boil. Now, boiling is an efficient cooling process. If you do this just right, the water boils and then the remaining water turns to ice. So it's possible to boil and freeze water simultaneously. And this is what happens if you put water in space. So the process of boiling cools the water being boiled, depends on the atmospheric pressure. Check, check. Both of those are right. It's a change of phase below the water surface. So the correct answer to this one is all of the above. And whenever you get a question like that, see that all of the above? That's a trap. Be careful. Potentially a trap. Now, melting occurs when a substance will change phase from a solid to a liquid, and of course, it's the opposite of freezing. When you apply heat to a solid, it causes the internal energy causes increased vibration, and this will eventually overcome the bonding forces holding the molecules together, and the molecules then break loose from their structure, and they slump or melt. So they no longer retain a rigid shape, and they melt. They become a fluid or a liquid. Freezing occurs when the liquid changes to the solid. It's the opposite of melting, obviously. And if you pull energy from a fluid, the molecules slow down. Eventually, the forces of attraction between them will allow them to bind together into a rigid shape, and we call that a solid. For water, that would be ice. Now, this page, you might want to copy into your notes somewhere. We're going to talk about energy and change of phase. And of course, if you go from solid to liquid to gas to plasma, you have to add energy. Okay, so because what you're trying to do is break the bond, and that takes energy to break the bonds. Okay, and that is, of course, you're adding energy, so the energy is absorbed from solid to liquid to gas, and the plasma be out here. It's not shown. If you go in the opposite direction, plasma, gas, liquid to solid, you have to pull energy out of the substance. The total amount of energy here, or any of these things, is the same. It's exactly the same. Doesn't matter which direction you go in it. Now, this is called a melting curve here, or a state curve. And basically what is it? This is for water. So this is, excuse me, the temperature in degrees C is on the y-axis, and the amount of energy is on the x-axis. Now notice this here, right here. This is by far the largest amount of energy. All the rest of these are relatively small. This one's whopping, and that's typical for most fluids. Vaporizing is almost always the most energetic process that the substance undergoes. It's especially true of water because water has polar bonds it's a polar substance. So it has bonds between the molecules that are unusually strong. And that's why it takes so much energy to vaporize water, because you're completely breaking those bonds. If you've ever held your hand underneath it or behind it when it's running, you'll notice it's warm back there. That's because the refrigerator has a cycle in it. And it pumps a special fluid that vaporizes and draws heat from the stored food. Okay, the fluid is circulated usually in thin tubes just under the skin inside the refrigerator. Okay, you can't see it. It's just inside the skin there. And this gas forms and takes away energy from the food, and then is directed to the condensation coil outside the fridge, where the heat is released back into the surroundings, and the fluid gets condensed back into fluid. And you can feel that heat if you hold your hand near the coil. Then the fluid is pumped back into the fridge to pick up more heat from the stored food. Air conditioners does the same thing. These things are called heat pumps or heat movers. And they're a kind of machine that will pump heat uphill, making cold things colder. So they pump heat from a cold area to a warmer area. And that's opposite the way heat likes to flow. Heat likes to flow from warm to cold. So air conditioners and refrigerators don't work when they aren't plugged in. You have to use energy to pump that heat uphill. When we talk about the second law of thermodynamics, we'll get that again. Now, the heat of fusion is the amount of energy needed to change any substance from solid to liquid or vice versa. So the heat of fusion for water is 334 joules per gram. And farmers use this idea. They place frozen tubs of water with unfrozen ones in their cellars to prevent jars of food from freezing. Okay, because in order to get the temperature really below freezing, you have to freeze all the water that's present. Farmers also will spray water in fruit orchards during cold snaps, because then what happens is the water freezes. The fruit has sugar in it, so it freezes at a slightly lower temperature than the water does. So the water freezes first, and you have to get all the heat out of that, and lower the temperature further. Because remember, water will stay at 0 degrees C as long as any water and ice present. The heat of vaporization, the amount of energy needed to change any substance from liquid to gas or vice versa. For water, it's a whopping 2,256 joules per gram. That means a little bit of water, about the size of a sugar cube. That's about 1 gram of water. It takes a whopping 2,256 joules to change to steam. This is why you want to have a wet finger if you touch something hot. The energy that would normally burn your finger, blow on your finger and burn it, instead vaporizes the water. Water's extremely high heat of vaporization makes it an excellent cooling agent. It also makes water good at putting out fires because it cools the burning material below the combustion temperature. It also has a tendency to cover the material and keep oxygen away from it. So phase changes, especially vaporization, involve a large energy flow because it takes a lot of energy to break bonds between molecules. The heat of vaporization is almost always larger than the heat of fusion. So for water, heat of vaporization is 2,256 joules per gram, and the water remains 100 degrees C throughout the process. The heat of fusion is only 335 joules per gram, and the water remains at 0 degrees C throughout the process. By contrast, it takes 418 joules per gram to heat the water from 0 to 100 degrees C through a temperature change of 100 degrees C. It takes 211 joules per gram to warm ice from minus 100 degrees C to 0 degrees C. It takes only 208 joules per gram to heat steam from 0 degrees C to 200 degrees C. By far the biggest one is this. When snow forms in clouds, the surrounding air is warmed because the change of phase is from gas to solid, and that releases energy to the surroundings, which involves the greatest number of calories, condensing 1 gram of 100 degrees C to steam at 100 degrees water, cooling 1 gram of 100 degrees C to 1 gram of 0 degrees C water, cooling from 1 gram to 0 degrees ice to near absolute zero are all about the same. Now, the heat of fusion for water ice is 80 calories per gram. The heat of vaporization for water steam is 540 calories per gram. This is just a different units. We're using calories instead of joules. That's why the numbers look different. Water has a specific heat of 1 calorie per gram degrees C, so it takes 100 calories per gram to heat water from 0 degrees C to 100 degrees C. Ice has a specific heat of 50 calories per gram degrees C, so it takes about 137 calories per gram to cool ice from 0 degrees C to minus 273 C, which is absolute zero. By far, the biggest thing is the first one, condensing 1 gram of 100 degrees C to 100 degrees water, because that's 540 calories. That's 5.4 times 100 calories for cooling 1 gram of 100 degrees C to 0 degrees water, almost 4 times 137 calories to cool ice down to absolute zero. That's because it's very hard to overcome the weak bonds between the water molecules to cause this change of phase. Water is an amazing substance. It has one of the highest heats of vaporization of any of the common liquids. You put ice in a picnic cooler to speed up the cooling of cans of beverage. You want to have the ice melt, because for every gram of ice that melts, 80 calories is taken from the beverage. That's why we use ice. When evaporation occurs in a dish of water, the molecules left behind are less energetic. They have decreased average speeds, and they result in a lower temperature. The correct one of these is all of these. When a relatively slow-moving molecules condense from the air, the temperature of the remaining air will tend to increase because you're taking away the slow-moving molecules. So that leaves the faster ones behind. We say an average molecular speed. You put a saucer of water on your table. What happens to the water? Well, it turns out it both evaporates and condenses at the same time. Some of the water, it's like an exchange. Some of the water is leaving, some of it's coming back. Which one of these wins depends upon what's going on around there. Okay, and we'll determine whether it's going to evaporate or not. Mainly the humidity in the air. The higher the humidity is, the more likely the condensation is occurring. When matter changes phase directly from solid to gas, we call the process sublimation. And this is what makes ice cubes disappear in the freezer. Now, where does the gas go? In the old-fashioned freezer, the gas deposits a crust on the walls of the freezer compartment, and then you had to remove it. We feel uncomfortable on a muggy day because water molecules are condensing from the atmosphere onto our bodies. And this makes us feel warmer instead of cooling because it interferes with the cooling effect of the evaporation of sweat. The dew that forms on a cold soda can when taken from the refrigerator is due to condensation. When warm, moist air blows over the Pacific Ocean and meets the cold waters off the coast of San Francisco, the result is fog. And this fog is really weird. I lived out in San Francisco for a while. And you see the fog would be sunny on one side of the street and cloudy on the other, and the fog would creep up the street. It was really spooky. Remember, fog is just a cloud that's on the ground. The process of boiling water tends to cool the water through evaporation. Boiling is basically just evaporation on steroids. Boiling and freezing can occur at the same time when the water is subjected to a decreased atmospheric pressure. Eventually, what happens if the pressure drops low enough, the water will boil. Boiling is a cooling process. The water will also freeze. That typically occurs at very good vacuums, almost space. Now, regelation occurs. Now, what is regelation? Regelation is when you basically cause the water to melt, the ice to melt under pressure, and then it refreezes. So what they typically do is they take a big block of ice, they put it outside someplace where it's really cold, and then they connect two heavy weights to a thin wire, and they put the thin wire on top of the ice. And what happens is the water expands when it freezes. So ice melts under pressure. So this thin wire puts a lot of pressure on this ice and causes it to melt. So the wire slowly works its way through the ice as it melts its way through. Meanwhile, the ice freezes behind the wire. So it refreezes behind the wire. So it looks really weird. It looks like you've passed the wire through the solid ice. And this is because ice has open structure. The same reason the ice floats on water and why it expands when it freezes. You want to make sure the radiator has antifreeze in it. You want to make sure you don't let your pipes get too cold. Okay, the melting point of a substance such as water is the same as the freezing point. Other substances are pretty much the same. When salt is introduced to water, the temperature at which freezing takes place is lowered. That's why we salt the roads in winter. If we lower the freezing point of ice, causes it to melt. It's provided the surrounding temperature is high enough. It gets really cold, that effect falls off. A common device that transfers heat from one location to another is any of these, all of the above. These are called heat pumps or heat movers. When steam condenses into water, the energy is released by the steam. When water turns to ice, the water molecules release energy. They have to cool off to slow down, so they release energy. When ice forms as freezing rain and clouds, the same question as when snow forms. Ice forming in clouds, okay, you're going from gas to solid, so it's releasing energy. Now that has to go someplace, so it warms up the surrounding air. Steam burns are much more damaging than burns from scalding water because steam contains more internal energy. When ice changes phase to become water, energy is absorbed. When a gas changes phase to become plasma, energy is absorbed. When a gas changes phase to become a solid, energy is released. And this is how snowflakes form in the air. Thank you very much. Please make sure you do your homework for this chapter. And if you missed any of these questions, please go over the material so that you don't miss them on the test.